Okay, so I'm also going to be talking about using OpenGL and WebGL specifically to do map rendering. I'm going to take a step back from Konstantin's talk and attempt to do like a crash course in the OpenGL pipeline. So forgive me, I'm going to talk relatively quickly. I'm interested in WebGL specifically for a couple reasons. First of all, taking the GPU acceleration and power that Konstantin talked about and dropping that into JavaScript, which is just exciting for me because web JavaScript programmers are not used to having that kind of power available. And the reason I'm interested in that is because I think that that doing GL rendering eventually will open the door to totally new types of mapping aesthetics and ways of visualizing data. So I got interested in this about 6 months ago, and I find it very exciting. The problem is just not enough people are really doing it. There's a few more projects now, certainly Konstantin's work and others. He mentioned Open Science Map, which is a great Android vector library. So part of the motivation for my talk was to just kind of go over the basics and hopefully pique people's interest and get them involved. So I'm going to do the Hello World example of OpenGL, which is to draw a triangle, and hopefully that will illuminate some of the core concepts and explain why OpenGL is a little different. And then we'll talk a little bit about how that can be applied to mapping. And this is a screenshot from the WebGL rendering project I've been working on that I will demo later. And it's not quite as much of a leap as you might think. There is quite a barrier just to getting a triangle on screen, but once you do that, you can make a polygon out of triangles, and you can make tiles out of polygons, and you can make a map out of tiles. So you really can start to build up hierarchical complexity rather quickly once you get the basics down. So the triangle. I think the easiest way to describe WebGL or OpenGL for me is as a kind of highly optimized hardware-assisted process for drawing triangles. And Konstantin went into this a little bit. It's you really are dealing with triangles. You can't even really draw lines or other shapes. And we'll talk about that a little bit later. So this is pipeline that goes from left to right here, where you provide kind of abstract geometric data describing your triangles. And then OpenGL kind of goes through those and assembles them into and figures out where to draw them on screen. And there are three parts of this process that you as the developer have control over. The first is providing the data, and the second is writing these two little programs called shaders that we'll talk about a little bit later, that kind of, as the data is being processed, your shaders are this kind of pre-processing step that the data is run through. And by manipulating the data, you kind of describe how that data should be drawn. So first of all, the data. If we want to draw a triangle, this is a representation of the OpenGL viewport coordinate system. So if you have a window that you want to draw into, the coordinates are always going to go from -1 to +1 for the entire screen, or the entire window you're drawing into. So 0, 0 is going to be at the middle, -1x on the left, +1x on the right. And this just gives you a simple resolution-independent way of specifying your coordinates, lets you work across many different devices, screen sizes, etc. So for the case of the triangle, we're just going to hard code our coordinates to these locations. We just want to drop a triangle in the middle of the screen, so we don't really need to worry about doing anything fancy. We'll just hard code these coordinates. We can do this in JavaScript using a feature called typed arrays, which is a relatively recent feature that was added specifically for WebGL. And in this case, it's a 32-bit floating point array. You can see it just looks like a standard kind of linear array. In this case, it's alternating x and y values, so defining three points, which are the vertices of our triangle. And this is how you communicate with WebGL. You would define these blocks of binary data. You actually have to specify to WebGL how the blocks are laid out. But this is kind of the simplest possible example. And because we're defining 3 points, we have one triangle. So now we get to the shaders, which is a word that you hear a lot with OpenGL, but I think is often not kind of explained. And I'll do my best. It's not necessarily straightforward. So shaders are basically small programs that are compiled and run directly on your GPU. So you provide the source code of those shaders through the JavaScript API or through another C-based OpenGL API. And they're written in a special language called GLSL, which is kind of just a C variant that has a bunch of built-in math functions for doing geometry manipulation. But once you pass them on to OpenGL, they're actually compiled and sent down to the GPU where they're executed. And they're highly parallelized. So you might have 20 or 40 of these, depending on your GPU, running at the same time because they're run in real time as the scene is assembled. And so they're also very localized. They only generally know about a very small amount of data that they're working on at that point in time. Unless you kind of take pains to send them other information, they don't know about your entire scene or your entire window or anything of that nature. So the first of these is the Vertex shader. And what happens is, once you provide your data to OpenGL, it's going to loop through all your triangles. And for each of those triangles, it's going to go through each vertex. And for each vertex, it's going to call your Vertex shader. So in this case, our Vertex shader is going to be called 3 times. And our Vertex shader is responsible for answering this question: where on screen should this vertex be drawn? In a more complex example, you might have kind of a 3D scene, and you need to say, you've had camera perspective, you want to kind of rotate your geometry into view, or pan it or zoom it around. In this case, we hard-coded our triangle data to be exactly where we wanted it to be, so we don't actually need to do anything. This is kind of the simplest possible vertex shader you can write. It just takes in the input position from our data buffer, and it just spits out the exact same position that it get in. So it doesn't do anything. It's a no-op. It does this by setting this special variable called GL-position. Okay, so the next step is the fragment shader. So once OpenGL knows where on screen you want to draw your triangle, it's going to go through this process called rasterization, where it's going to fill that in, figure out which pixels make up this triangle. And for each of those pixels, it's going to call the fragment shader. So you can see that the fragment shader is like a super parallelized program. It's going to be called, like in many cases, millions of times per second if you're doing like 60 FPS rendering. And the fragment shader is responsible for answering this question, which is what color should this pixel be? So again, we're going to do the simplest possible fragment shader. This is a fragment shader that just sets everything to red. So this is just a red color fill fragment shader. It does this by setting a special variable called GL-frag_color, which is how the shader outputs. And it sets it to a 4-component vector with red, green, blue, and alpha values. And if we do that, that's kind of the basics that we need to get a triangle on screen. So now we can go back to the Vertex shader and talk a little bit about how we can use the shader to do some simple manipulation. So you can see I added a few lines to copy the position that was sent in and just multiply it by 0.5, which is going to scale it down to half the size, and then also adding 0.5 to the x and y coordinates to move it, and I'm spitting out that modified value. And if you do that, you go from this to this. So this is obviously a very simple example, but hopefully gives you some idea of the way you can use the Vertex shader to do kind of manipulation of the geometry as it's drawn. So in the case of a map, as we'll talk about later, you would be using this to kind of pan and zoom the tile geometry around to the appropriate position. We can do the same type of thing in the fragment shader. We can use another special variable called GL-frag_chord, which is the location of this pixel on screen, and we can actually map that to the color so that we can kind of map the position of the pixel to its color. Again, this is just kind of a representative example. So we're mapping the x axis to red, and we're mapping the y axis to green. And if we do this, we can go from this red triangle to something that looks like this, which hopefully even seeing like a little gradient gives you a hint of like, you can use lighting calculations in the fragment shader to do interesting things. Okay, so those are the super basics of how you get a triangle up. So what are you going to do if you want to actually draw a map with this? Well, first of all, you've got to get some data from the server, and the way to do that, as the past two speakers have been talking about, is through vector tiles. I won't really spend a lot of time on this since I think the ground has been pretty well covered. Basically, just the idea is to get your raw geometry data back from the server to cover whatever tile area you're requesting. I personally recommend just doing this in GeoJSON if you're just experimenting with this and getting started. There are a number of kind of optimized binary formats that I think make sense for production use. But if you're just kind of playing around with this stuff, GeoJSON is great because it's human readable. If you're kind of loading this in the browser, you can open the XHR request and see what geometry you got back and debug more easily and things like that. So in this case, I just took a sample GeoJSON tile. I threw it onto GeoJSON.io to kind of give you a sense of what it is. In this case, it's just a bunch of building outlines that are kind of gray shaded there in Lower Manhattan. And that's just the basic ideas. You got kind of squares of geometry that you reassemble. I got this particular one from this service we've been using internally for development at Mapzen, but I'm actually, right now, we're actually kind of publicly making it available to people. So please go check it out, mapzen.com/vector. It's still, again, I wouldn't use it for a production application, but I think it's great as a development resource. Has a worldwide planet file that we update daily. You can use your standard tile coordinates. to get geometry that's clipped and simplified to whatever zoom level you need. There's no API key sign up or anything, so you can just go try it out. Definitely would like to get feedback from people about it. And it tries to be agnostic. Our goal with it is for it to be a tool for people to experiment. So it serves in GeoJSON and topo-JSON. It also serves in the kind of Mapbox flavor map-think vector tiles that are used in tile-mill 2. So same thing that Andy talked about earlier, and used in Mapbox GL. And it also serves in the Open Science Map protobuf format, which we've been using for an Android app that we're developing. As an alternative, this work came out of this OpenStreetMap US hosted service that Mike Nagurski created. That is a kind of fork of TileStash that has predominantly GeoJSON vector tiles. So we based our work on his, and this is certainly available to you as an alternative if you would like. Okay, so now we have our Polygons client side, but we have a problem, which is that OSM data tends to be complex polygons like this. That in many cases have holes in them, for example. And the problem is, we kind of touched on earlier, is that OpenGL can actually only draw triangles. It doesn't know how to draw more complex polygons, which is often surprising to people when they hear that, because they ask, like, why could what's supposed to be a very advanced graphics API not know how to draw anything other than triangles? But I think as Konstantin kind of hinted at, OpenGL is really meant to be a very low-level library. It tries to do kind of highly compatible, portable process for doing very simple things, and then shifts the complexity to the developer. So the result is that we need to go from, and also if you're just implementing triangles, you can obviously make all sorts of optimizations, right? Because they're the simplest polygon. You can make assumptions. You're basically making hardware for the purpose of drawing triangles. So there's a lot of obvious advantages if you're thinking about that side. So what we need to do is go from the complex polygons to triangles, which is a process called tessellation or triangulation. And it is a pretty interesting math problem. Luckily, it's been solved for us by a number of people. There's kind of a pretty standard algorithm that comes with the OpenGL utility library for doing this. And there are actually 3 very good JavaScript ports of that algorithm. So you can use any of these 3 fairly interchangeably. And they're generally as easy as just kind of passing in the list of coordinates for your complex polygon and getting out a list of coordinates for your triangles. So I don't have time to go into all the details of this, but what you would do at this point is you would go back to your Vertex shader, and you want your Vertex shader to do something like this. You have your viewport, you kind of lay out your tile grid just like you would with raster tiles. You identify where you want this particular tile to go, and then you want your Vertex shader to basically kind of squish the data into that space, which generally speaking is just a matter of kind of multiplication and arithmetic, just kind of moving, scaling it down to the appropriate size based on your zoom level, and translating it into the correct position. So that's what I've been working on for the past few months. And I wanted to demo the result of that, which is a library I've been working on called Tangram, which is kind of library for visualizing OSM data with WebGL. Again, it's definitely experimental and early, and notably has no labels whatsoever due to all the complexities that Konstantin talked about. I've been focused very much on just kind of rendering core geometry, and Konstantin is correct that there are many difficult elements you need to kind of bring this to complete fruition as an alternative. Let's see, I think I have to turn mirroring on here. Okay, I think that'll do. Okay, so here's an example. This is a WebGL rendered map based on, in this case, it is consuming GeoJSON vector tiles, so it can also consume other formats. We can zoom in, get some more detail. You can start to see there's some 3D building detail here from the OSM simple 3D building tags. And again, because this is client-side, we can control the style. So we can go to this kind of simple style sheet, and I can comment out one style, reload the page, and get randomly colored buildings as an example. It's good for debugging. Okay, so those are the basics. And I wanted to talk, let's see, I'll just go back here. I wanted to talk specifically about why, what's going on here? Sorry. I wanted to talk about what I think is interesting about this. To me, what's interesting is kind of applying the shader mentality to drawing maps, to allow you to do some kind of unusual things. So, you know, we saw you can do kind of your standard 3D perspective here. You know, you get your 3D buildings as you pan around. But you can also, in the Vertex shader, with really just 2 or 3 lines of code in a lot of cases, do things like an alternate perspective, like you know, kind of SimCity style isometric view, which is useful for some cases. You can also do more unusual things. You can displace the vertices into kind of, you know, unnatural locations for different effects. So one I like is this effect I call the pop-up, where the geometry is actually 3D in the middle of the screen and actually fades at the edge of the map. And, you know, it's not like I have a particular use case in mind for this. I think it's just a cool demo of the types of things you can do that would be like very difficult to do without this level of client-side control. Could also do some animation. So we can do, this is what I call the elevator buildings, animating the building height by time. Again, another good debugging tool. Or you can do kind of like a wave application where you just kind of deform the geometry by a sine wave. And again, these are, the point of these examples is mainly to show that you can do things that are just very different from the kind of style sheet way of thinking. And this kind of is, this is my particular interest, is seeing people do the kind of adopt the OpenGL programmable pipeline way of thinking. Lastly, you can do the same kind of effect in your Fragment shader. So you can use your Fragment shader to do algorithmic textures. In this case, I did a kind of what I call water animation. It doesn't look much like water, just uses Perlin noise. It has kind of a 90s demo scene aesthetic to it. But again, an example of the kind of thing you can do if you have this kind of procedural control. You know, there's many variants of this. Been working on kind of like a little night shading kind of variant. And again, you know, you have a lot of control over this because it's all client-side. So especially once you have your geometry down in the browser or on device, you can change all these things at will without any other kind of impact. I will, I think, let's see, there's one more. Can you actually see these? No, how can I get this thing over here? So that is where I want to stop. These are two, this first, I definitely encourage you to please, you know, hopefully your interest is piqued a little. I'd love to see more people playing with this stuff. This first link is the best WebGL tutorial that I have found for this stuff. And it's very WebGL specific, which is kind of rare. The second one is a generic OpenGL tutorial, but it's also quite good. And that is it. So I'm here for the rest of the conference and would love to talk to people about this stuff. Also be here for the hack day. So, you know, if you want to talk about WebGL or OpenGL, or maybe check out the vector tile service I mentioned earlier, give us some feedback about how we can make it more useful to people, that would be great. Thank you.
A quick question. So, in particular, the live demo we saw a moment ago looked really impressive, and that a browser can do that. But what kind of power do you need on the machine? Will a phone already do that kind of thing, or is there a constraint?
Well, this is a MacBook Air, and generally, like a laptop or desktop machine will have no problem with this stuff. It's much trickier on mobile device, which we certainly have interest in doing. So, and I've been working in WebGL, and WebGL support, you get kind of an extra penalty if you're doing WebGL on mobile. You can do it, and I think it will get a lot better. If you're doing straight OpenGL, you have a better shot. For instance, Open Science Map that I mentioned earlier, we've been using that on Android, and it has extremely good performance on kind of, you know, fairly middle-of-the-road Android devices, I think. But on the WebGL side, it's going to take a while, especially to do things like the procedural texture. That's just pretty intensive.
That's it? Yep.
Last chance.
I think
Okay.
this is people are still recovering from your pace. It was a lot, but yeah, I'd love to see more.
Great. Thank you.